Okay, perfect. So welcome everyone to the virtual seminar on geometry with symmetries. So it's a pleasure to have Sergio Zamora Barrera from Oregon State University. And he is going to talk about the topology of manifolds with almost non-negative curvature and maximum rank and their Gromov-Hausdorff limits. So uh, thank you, Sergio, for
Yeah.
giving a talk. So.
Thank you, Fernando, for the introduction and, of course, for inviting me to speak here. So yeah, we'll talk about this long title. And what it actually means is the torus, topology of the torus, and things that look like the torus and things that feel like the torus. So I will start talking about these three very classical theorems about the flat torus. Um, One of them is by Bochner that says if you have a compact n-dimensional Riemannian manifold and we know that the Ricci curvature is non-negative, then we can put an upper bound on the first Betti number is actually less or equal than the dimension. And he actually proved that in case the first Betti number equals the dimension, then X is actually a flat torus. We have also a result by Bieberbach that says if you have a compact Riemannian manifold with zero sectional curvature, so essentially what we call flat, then there is a covering space X prime that is a flat torus. So X may not be a torus itself, but is covered by a torus. And then there is a consequence of Mailer's compactness theorem that says that if you have a sequence of flat Riemannian manifolds, Xi, all of them homeomorphic to the n-dimensional torus, and the sequence Xi converges in the Gromov-Hausdorff sense to a limit space X, then that limit is going to be again a flat torus. So I would like to go over more modern versions of these theorems and take a look at their proofs because it's funny that these proofs share very similar ideas, and I want to highlight those ideas. But before that, I would like to take a short detour into what I mean by this Gromov-Hausdorff convergence. So the Gromov-Hausdorff distance is a metric in the space of compact metric spaces modulo isometry. And it's like the right notion of convergence when we say one metric space converges to another metric space. And it has many convenient properties. And we can see some examples in here of what I mean by a sequence of metric spaces converging to another metric space. We can obtain the sphere as a limit of a sequence of finite metric spaces, or the sphere as the limit of Riemannian metrics on the torus. So we can take the torus and deform it to look like a sphere. And these two examples should at least tell you that when you have Gromov-Hausdorff convergence, you should not expect the topology of the limit space to be the same as the topologies of the elements of the sequence. In general, we can say very little about these, about the topology of the limit space in terms of the topologies of the elements of the sequence and vice versa. But one nice property that we always have in this space of compact metric spaces equipped with this metric is that if we fix parameters n, k, and d, then when we look at the space of n-dimensional manifolds with a lower bound on the Ricci curvature and an upper bound on their diameter, then this set is pre-compact with respect to this distance. In other words, if you take a sequence of Riemannian manifolds of the same dimension, such that all of them share a lower bound on the Ricci curvature, then you can always find a convergent sequence, a convergence of sequence in this sense. So there will be some limit metric space that is definitely not a Riemannian manifold because, well, as you can see from these examples, we do not expect the topology to remain when we pass to the limit. Sorry, I don't see the. Sorry, I messed up something. View. I kind of lost all the people, so I don't. Well, I guess I
We're
will give
still
my
here,
talk like that.
yeah.
Yeah, sorry. Yeah, sorry. I just lost the tiny window with the our faces. but I guess I will live with that without that. So please let me know if you have questions. I don't see some right now for some reason. Okay. And yeah. And of course, this is a symmetries seminar, so we will be very happy to know that there is an equivariant version. So now we have a similar notion for pairs xg, where x is a compact metric space and g is a compact group of isometries of x. So we have a notion of convergence of spaces with groups acting on them. And it is compatible with taking quotients. So it's very much what we expect if we have a sequence of pairs of spaces and groups converging to a space and a group, then the sequence of quotients will converge to the quotient in the limit. And we have a very basic example in here of a sequence of actions by cyclic groups that converge to an action by S1. So we have different actions of different groups on different spaces, but there is a kind of like a clear notion of convergence here. And this is what we call the equivariant Gromov-Hausdorff convergence. And then this, I will show you a more complicated example right now. One of the most standard constructions for the p-adic numbers is a limit in this sense. So in this case, I have the three adics constructed as a limit of a sequence of cyclic groups. So we start with the group of 3 elements and group of 9 elements, then 27, and so on. And we just like equip them with metrics that look like this. We separate them in like blocks of 3 at each time. And then in the limit, what we get is the 3 adics. And you can do this, of course, with any p. So there is like this notion of convergence of compact groups of compact metric spaces equipped with compact groups of isometries. And this works out very, very well for compact spaces. But there is also a version for non-compact spaces, which we call the pointed Gromov-Hausdorff convergence. So now this is a metric in the space of pointed proper metric spaces. So we look at all these proper metric spaces, so in particular all complete Riemannian manifolds, and equip them with one point. This is like a giant space, but there is a metric in this space that is again coherent with what we think of when we say, oh, a sequence of metric spaces converges to another metric space. Like in this picture, I can produce a sequence of ellipsoids that converges to a cylinder. So notice that if you look at a large ball around the base point, so the base point is the red one marked in here, will look very similar to a ball of the same radius in the limit space. And this metric now in the space of pointed proper metric spaces will still again have this compactness property that if you look at the space of all n-dimensional Riemannian manifolds with a lower bound on the Ricci curvature, then this set is going to be again pre-compact. So any sequence will have a convergence subsequence. And this pointed Gromov-Hausdorff distance that we use for non-compact spaces, again, has its own equivariant version. So this is like the one that we use the most. We have the space of triples, xpg, with now we have a proper metric space with a favorite point p, and it's equipped with a closed group of isometries. Then we have a metric on this space of triples that we relate when two metric spaces look very similar and the actions on these two spaces look very similar. And this again has a coherence property that if you have a convergence of spaces and groups, then you also have convergence of the quotients. So we have all those versions of Gromov-Hausdorff convergence, the Gromov-Hausdorff convergence for compact metric spaces, equivariant for when you have compact metric spaces equipped with groups of isometries, pointed Gromov-Hausdorff convergence when we want to deal with non-compact spaces, and this pointed one also admits an equivariant version. For example, let me show you in here what do I mean by this coherence. We can have a sequence of constant metric spaces. So I have the space R2, the space R2, the space R2, the space R2. The sequence of spaces is constant, but I can equip them with different groups of isometries. So I equip them with groups Gn, where Gn is just a copy of the integers acting by vertical translations. So if I make the vertical translations act more finely each time, I can make this sequence of actions by vertical translations converge to the action by R by all vertical translations. And if we do that, the sequence of triples of R2 equipped with these groups will converge to R2 equipped with this set of all vertical translations. And then in this case, the sequence of quotients will be just cylinders, will converge to the quotient in the limit space that would be just a line. So this is what we mean by this coherence property, that passing to the limit and then taking the quotient will be the same as first taking the quotient and then passing to the limit. So after that detour, I would like to go back to these three theorems, Bochner theorem, Bieber-Bach theorem, and Mela theorem, and look at their more modern counterparts. And as I said before, I would like to take a look at their proofs and to kind of like point out where they actually feel the same. Any questions right now? And again, sorry, I cannot see you, so please interrupt me if there's a question. Yeah. Okay. So yeah, I would like to start with the Bochner theorem. So a more modern counterpart will be the one given by Gromov and Chigger and Kolding that replaces non-negative Ricci curvature by almost non-negative Ricci curvature. So they show that you have a compact n-dimensional manifold, and the Ricci curvature is greater or equal than some small minus epsilon that is given by the dimension and the diameter of the space. So in some sense, almost non-negative Ricci curvature. Then we arrive at the same conclusion. The first Betti number is at most the dimension, and in case of equality, X is diffeomorphic to the torus. Of course, it's not exactly the flat torus as before, but is at least diffeomorphic. Now I put Gromov and Chigger and Golding here. Gromov proved the first part, that under these conditions, then you have the upper bound on the first Betti number. And then Chigger and Golding show that in case of equality, then the space X is diffeomorphic to Tn. Actually, it was first proven by Kolding that the X is homeomorphic to Tn. And then between Chigger and Kolding, they proved together that it's actually diffeomorphic. So the proof idea is actually starts with very simply. You just take a contradicting sequence. So you negate the theorem, and that produces a sequence of spaces xi, which by some very simple rescaling arguments, you can assume that converges to a point, meaning that the diameters of the spaces converge to zero. So they become smaller and smaller. And also the Ricci curvature is almost non-negative. And what they do is just find finite sheeted covers. So they start with xi and produce covering spaces xi prime in such a way that they converge in the Gromov-Hausdorff sense to some k-dimensional torus with k at least the first Betti number of the xi's for large I. And of course, a very important tool that is used in here is that again, this sequence of covering spaces xi primes share this dimension and lower Ricci curvature bound. So this allows one to find a subsequence that converges in the Gromov-Hausdorff sense. And then thanks to all the symmetries that we have in here, of course, notice that the fundamental, that this sequence can be taken to be normal coverings, meaning that we have these nice groups of isometries given by the deck transformations. So this nice amount of symmetry passes to symmetry in the limit, and that is why the limit is so symmetric and so nice. So yeah, as I said before, it converges to a torus. They managed to prove that the limit is a torus. And moreover, sorry, I missed something. The limit is a torus, and K, the dimension of this torus, as I said before, is at least the first Betti number of the xi's for large I. And then, as I said before, this theorem was proven separately by Gromov and Chigger and Golding. Gromov proved the first part. So the first part amounts to showing that K is at most the dimension n. So this was done by packing arguments using the lower bound on the Ricci curvature. And basically, he showed that if you have this sequence of manifolds of dimension n and they converge to some other space and they share a lower bound on the Ricci curvature, then the limit space cannot have more dimensions than the sequence. And for the second part, Chigger and Golding assume that K equals n, and they develop tools to show that if you have a sequence of Riemannian manifolds with a lower bound on the Ricci curvature that converge to another Riemannian manifold of the same dimension, then you can actually extract diffeomorphisms from these Gromov-Hausdorff convergence. And uh, this is how they show that these xi primes are actually diffeomorphic to the n-dimensional torus. And then later, this theorem was proven for RCDKN spaces, which are non-smooth versions of a Riemannian manifold of dimension n and Ricci curvature with a Ricci curvature lower bound. So this, like the non-smooth counterpart, was obtained by Ilaria Mondello, Andrea Mondino, and Raquel Perales. Any questions right now? Okay. Now I'd like to look at some descendant of Bieber-Bach theorem. So remember, Bieber-Bach theorem states that if you have a Riemannian manifold with zero sectional curvature, then it has a covering space that is a torus. This theorem was kind of like modernized by Gromov, who proved that if you have a compact Riemannian manifold, but rather than having zero sectional curvature, it has almost zero sectional curvature. So the sectional curvature is bounded in absolute value by some small number depending on the dimension and the diameter. I didn't say it in here, but I mean it has an n-dimensional Riemannian manifold. I think for the rest of this talk, n denotes the dimension of the manifold. um, and yeah, what Gromov showed is that if you have a Riemannian manifold that has sectional curvature almost zero, then it admits a covering space that is a nil manifold. So it's not exactly the same conclusion like before, but it's something very similar. So what is a nil manifold? A nil manifold is something that looks very similar to a torus. I call these the cosines of the torus. So a nil manifold is a quotient G over lambda, with G a simply connected nilpotent Lie group and lambda a co-compact lattice. In other words, a discrete subgroup of my simply connected nilpotent Lie group such that the quotient is compact. And of course, the most natural example of this is the torus. You can take G to be Rn, lambda to be Z to the n, and then the quotient is the torus. The torus is a nil manifold, where you can produce different nil manifolds. The most basic example is obtained by looking at the group nil. So nil is the space of upper triangular matrices with ones on the diagonal, and nil Z is n by n matrices with ones on the diagonal and integer coefficients. And sorry, these this happens to be a lattice in this group. The group on the left is not hard to see that it is contractible and nilpotent. And then the quotient is what we call a nil manifold. And in this case, it will have dimension m times m minus 1 over 2. And it's actually possible to show that any nil manifold actually doesn't look very different from this one, because any simply connected nilpotent Lie group happens to be a subgroup of one of this form. And once we have a nil manifold, its fundamental group is going to be lambda because G is simply connected, and if it's obtained as G over lambda, then lambda is the fundamental group. It's a finitely generated nilpotent group. And when we have a finitely generated nilpotent group, what we have is a tower of subgroups. So we have subgroups lambda 0, lambda 1, lambda 2, lambda j, blah, 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 with the property that each quotient is abelian. So if I take one of these and I quotient out by the previous one, it's going to be abelian regardless of j. This means that if I go to this tower and I take two elements A and B at some level of the tower, their commutator is going to be at least one level below. And then the rank of the nilpotent group is defined to be the sum of the z factors in these abelian quotients, lambda j over lambda j minus 1. So you take each floor of the tower, you quotient out over the next floor, you get an abelian group, and then we just count the number of z factors. For example, if this is our lambda, the upper triangular matrices with integer coefficients, 4 by 4, this one has a tower of subgroups consisting of the trivial group, the group that has only non-zero integers in the corner, the ones that have non-zero integers on this on the next layer, and then the ones on the next layer. So in this example, it's actually super easy to compute that if you take a commutator of two elements in one layer, you end up in the next layer. Sorry. You end up in the next layer. And we can count like what is the rank of this group. And this is like 1 in here, 2 in here, and 3 in here. So this is just 6. This is kind of like the number of these that we need to produce our group. And yeah, that's the rank of a nilpotent group. We'll use that later. So now that we've gone over like what is a nil manifold, I want to highlight this theorem of Gromov that says, well, if you have a compact Riemannian manifold that has almost zero sectional curvature, then there is a covering space that is almost a torus. In this generalized sense of like a quotient of a simply connected nilpotent Lie group by a lattice. But this condition on the sectional curvature happens to be very strong. So I think we know that bounds on the sectional curvature are really hard to obtain. Something more general would be a lower bound on the Ricci curvature. And Kapovich and Wilking recovered a version of this previous theorem at the level of fundamental groups. So they show that if you have a compact Riemannian manifold and has almost non-negative Ricci curvature, so they replace the almost zero sectional curvature by just a lower bound on the Ricci curvature, then they show that there will be a compact covering space, X prime, that is not necessarily a nil manifold, but has a fundamental group that is kind of the one of a nil manifold because it's nilpotent of rank at most the dimension. And they show that in case of equality, if the rank of this nilpotent group by 1 of X prime is equal to n, then X prime is homeomorphic to a nil manifold. So of course, I would like to draw parallels to both between this theorem and Gromov-Chigger-Kolding theorem that said if you have almost non-negative Ricci, then the first Betti number is at most n, and in case of equality, your manifold was diffeomorphic to a torus. Now they replace first Betti number by one of this compact covering space, and they replace the torus by a nil manifold. This theorem happens to be a little bit more general because the rank of a nilpotent Lie group is always larger or equal than the first Betti number. So in some aspects, this theorem implies the other one. And this was actually improved to diffeomorphism. So what Kapovich and Wilking proved was that if you have this compact covering space whose fundamental group had rank exactly n, then this covering space X prime is homeomorphic to a nil manifold. Kong, Rong, and Xu show that if you have this equality of ranks, then your space is diffeomorphic, not only homeomorphic to an L manifold. And this proof is like somewhat technical and uses Ricci flow, something that is not available when your space is not smooth, for example, in the context of RCDKN spaces, these non-smooth analogs of Riemannian manifolds. And all of these results were again proven in that context. So the three different groups give three proofs of the three statements above without using smoothness. So meaning that our proofs apply to RCDKN spaces. So I put three groups of people in here: Broya, Green, and Tao, Xingyu Zhu, and myself, and Jikan Wang. So Broya, Green, and Tao showed the first part about the existence of this uh, compact covering space X prime that has fundamental group that is nilpotent of rank less or equal than n. Actually, their proof is very non-differential geometric. It's mostly combinatorics and group theory. Then Xingyu Zhu and myself prove that in case you have this pi1 of x prime nilpotent of rank less or equal than n, then this space x prime is homeomorphic to a nil manifold in the non-smooth context. And then Jik and Wang proved the diffeomorphism part in the non-smooth context. But what would I mean by diffeomorphic? Well, when we're talking about non-smooth spaces, we mean bi-Hulda homeomorphic. But also another feature of Wang's proof is that in the smooth context, so what Jik and Wang achieved here is that he gave proof of the diffeomorphism of the second part. So he showed that if you have a smooth Riemannian manifold like the one in Kapovich and Vielking, and you take this compact covering space that has rank equal to n, so whose fundamental group has rank equal to n, then he showed that X prime is actually diffeomorphic to a nil manifold without using Ricci flow. So that's the feature of his proof. So I would like to go over the proof idea of that second part, the part where we assume that the rank of this fundamental group is equal to n, and then what we do to show that this X prime is homeomorphic to a nil manifold. And the proof idea starts exactly the same as before. We assume that the theorem is false and pick a sequence xi that contradicts the statement of the theorem. And of course, again, one can take them such that the diameters go to 0. So again, I have a sequence of spaces xi that converges down to a point in the Gromov-Hausdorff sense because their diameters go to 0. And what we do is take these universal covers, and we were able to show that if you have this equality of rank, this pi1 of x prime, have rank equal to n in some if basically we show that if these xi's admit a compact covering space whose fundamental group is nilpotent of rank n, then we are able to show that xi primes converge to Rn. And after that, what we do is a sequence of constructions. First, we find finite index subgroups of the fundamental groups of xi that are torsion-free and nilpotent. So of course, we think of pi1 of xi as a group of isometries of xi tilde acting by deck transformation. So we find a nice subgroup of isometries that is nilpotent and torsion-free. And this allows one to apply Malchev theorem to say that there exists a simply connected nilpotent Lie group Gi that has lambda I as a lattice. And now that step produces a nil manifold, the nil manifold being Gi over lambda I. So ultimately what we want to show is that the quotient of xi tilde over lambda I is homeomorphic to a nil manifold. which nil manifold gi over lambda I. And now this is where we use very heavy topological machinery by Farrell-Xiang and Friedman and Quinn and Perelman, who all three together in different dimensions, Perelman in dimension 3, Friedman and Quinn in dimension 4, and Farrell-Xiang in dimensions 5 and greater, that if you have a topological manifold that is homotopy equivalent to a nil manifold, then your original topological manifold is actually a nil manifold itself. So all we had to show is that this quotient xi tilde over lambda I was both a topological manifold and homotopy equivalent to a nil manifold. Now we have the topological manifold part because of the regularity results established by Jigger and Colding. So what we had to show was that these quotients xi tilde over lambda I were homotopy equivalent to the nil manifolds that we want them to be homeomorphic. Um, and nil manifolds are aspherical, meaning that their universal cover is contractible because the universal cover of a nil manifold is a simply connected nilpotent Lie group, and simply connected nilpotent Lie groups are contractible. So this essentially amounts to, so showing that a space is homotopy equivalent to a nil manifold amounts to show that their universal covers are contractible. And then basically our goal turned to be to showing that these spaces xi tilde were contractible with the information that we have that they converged in the pointed Gromov-Hausdorff sense to Rn. So what we did from here was to find pointed Gromov-Hausdorff approximations, but not to Rn, but to the groups Gi with some appropriate left invariant Riemannian metrics, and with the additional property that these Gromov-Hausdorff approximations were lambda I equivariant, because this lambda I acts on both spaces. Lambda I acts on the Lie group Gi just by the virtue of being a subgroup, and lambda I acts on xi tilde because it's a group of deck transformations. So we found lambda I equivariant Gromov-Hausdorff approximations, and with those we are able to show using homological arguments that these xi tildes are actually contractible. And basically putting all of that together shows that when you have a compact Riemannian manifold with almost no negative Ricci curvature and rank equal to the dimension, and there is a compact covering space with nilpotent fundamental group and rank equal to the dimension, then this compact covering space X prime is actually homeomorphic to a nil manifold. So that's where Xingyu Zhu and I got stuck, proving that this X prime was homeomorphic to a nil manifold. And there is a technique that one could have used that it's the same technique that Chigger and Colding applied in here, which is take a sequence of covering spaces that doesn't collapse, meaning that the sequence converges to a space of the same dimension. This is what Chigger and Colding had for when they developed their Reifenberg arguments. Now, one can do that in this setting, taking finite sheeted covers that don't collapse. But if one does that in here, their diameters of those finite sheeted covers go to infinity, and basically one loses control of the pointed Gromov-Hausdorff convergence. So we believe that to be useless, but Jik and Wang proved us wrong, who basically did that approach again, constructed a sequence of finite sheeted covers xi prime that have diameters going to infinity. So in the Gromov-Hausdorff sense, they kind of like get lost in the space. However, these lambda I primes still act on the spaces Gi because this lambda I is lattice in the group Gi. So there is still a nil manifold somewhere in here, Gi over lambda I prime. And what he was able to manage to get is an equivariant diffeomorphism between this large, massive, compact, finite sheeted cover and this massive submanifold in a way that is equivariant with respect to these group actions that make the quotient exactly the space that we were considering originally, xi tilde over lambda I. So he basically took what we said, oh yeah, that's useless, and show that, yeah, no, actually that's how you prove it, and that's how you actually prove get the diffeomorphism part of Kapovich-Wilking theorem without using Ricci flow. So he basically proved these results by Huang, Kong, Rong, and Xu without these smoothness tools. And of course, he relies on very technical theory developed by Chiger, Jiang, and Neighbor, but still is very impressive. And again, we're kind of like feeling always in the same boat of like trying to construct these covering spaces and abusing the symmetry of the covering spaces to get some information about the topology of the basis space. That's it. Now I would like to move to the modern counterparts of Mailer's theorem. Mailer's theorem was a sequence. If you take a sequence of flat Riemannian manifolds, homeomorphic to Tn. So by flat here, of course, I mean sectional curvature equal to 0. Then any Gromov-Hausdorff limit is again a flat torus. So there is a modern counterpart to that. It's not exactly the same theorem, but Perelman showed that if you have a sequence of compact n-dimensional Riemannian manifolds with a lower bound on the sectional curvature and a lower bound on the volume, then if they converge in the Gromov-Hausdorff sense to some limit space, then that limit space is homeomorphic to the spaces xi for large I, meaning that the topology stabilizes. The sequence, the limit of the sequence actually has the same topology as the topology of the limit is the same as the topology of the elements of the sequence. So it's basically the picture that I showed you at the beginning, that doesn't happen. The topology stabilizes whenever you have a lower bound on the sectional curvature and a lower bound on the volume. So basically what when we specialize this theorem by Perelman to spaces homeomorphic to the n-dimensional torus, it says that if you have a sequence of n-dimensional Riemannian manifolds homeomorphic to the n-dimensional torus, if they share a lower bound on the sectional curvature, then any Gromov-Hausdorff limit has to be again homeomorphic to the n-dimensional torus. And then one can ask if the same is still true when the sequence collapses, meaning that these volumes go to 0. So this was asked by Petrunin and recently solved by Elia Broe, Aaron Neighbor, and Daniela Semola, who showed basically that you can, if the spaces xi are tori, then you can remove the non-collapsing condition, meaning that the volumes can now go to 0. Then any Gromov-Hausdorff limit is again homeomorphic to some torus of smaller dimension. So again, I would like to highlight the ideas of this proof because it will feel very similar to what we've been doing before. So again, they show that if you have a sequence of spaces xi that are each homeomorphic to the n-dimensional torus, and they share a lower bound on the sectional curvature, then their Gromov-Hausdorff limit has to be, again, homeomorphic to some torus. So they basically do these tricks that we've been doing, find covering spaces xi prime with the property that they don't collapse, so their volumes don't go to 0, but at the same time they don't blow up, meaning that their diameters remain bounded. And by those compactness properties of the Gromov-Hausdorff convergence, one can find a sequence that converges in the Gromov-Hausdorff sense to some limit space. But because the sequence doesn't collapse, by Perelman's theorem, one guarantees that this limit space is homeomorphic to the, again, to the n-dimensional torus. And then in this particular case, one can show that when they take the universal covers, the limit of the universal covers is going to be the universal cover of the limit. That doesn't happen very often, but happens in this situation. And now by this compatibility of the equivariant pointed Gromov-Hausdorff convergence, we have the following. All these groups of deck transformations converge to some limit groups acting on these spaces that we know are homeomorphic to Tn and Rn. And I know that the space we're interested in, the one that we want to show that it's a torus, is obtained as a quotient of x prime by some abelian group action and Rn by some abelian group action. Why abelian? Well, because the groups of deck transformations in these spaces xi prime and xi tilde are abelian, so their limits have to be again abelian. So this essentially exhibits the limit space as a quotient of the torus and as a quotient of Rn by abelian groups. And here the proof kind of like has two parts. First one is that they have to show that the space is homotopy equivalent to the torus, and to show that it is a topological manifold. Again, by this very strong topological results that I mentioned before, this would amount to show that X is a torus. So these two results together imply that X is homeomorphic to an m-dimensional torus, being a topological manifold and being homotopy equivalent to the torus. And these two parts are very, very different. So the first part, showing that the space is homotopy equivalent to the torus, for using the fact that I can express it as a quotient of the torus and as a quotient of Rn, is just some basic topological arguments, nothing super crazy. And then the second part, the showing that X is a topological manifold, actually uses the smoothness of the Riemannian metrics and the geometry of the lower bound on the sectional curvature. That is using results by Vitaly Kapovich about the regularity of Gromov-Hausdorff limits of smooth Riemannian manifolds with a lower bound on the sectional curvature, and how the geometry of quotients behave using results of Catherine Searle and Fernando Galaz. So yeah, the second part is very, very delicate, while the first part is very general and very topological. And to highlight how delicate the second condition is, Vitaly Kapovich showed that if you remove the smoothness hypothesis, then this theorem breaks. So he basically constructed an example, which is actually easy to construct. You start with a Poincare sphere, you take the suspension, you take connected sum with a four-dimensional torus, and then multiply by S1, and then take the S1 fiber, go to 0. These are essentially five-dimensional tori that have a lower bound on the sectional curvature in the synthetic sense, what are known as Alexandrov spaces with a lower bound on the sectional curvature. But the limit is not a topological manifold. The limit is like this thing in the middle. So basically what this example highlights is the importance of the smoothness of these Riemannian metrics in this torus stability. So this shows that this problem is actually more delicate than what one may think initially. And in here, I would like to ask, point out that, we've been talking about lower Ricci curvature bounds all the way, and now we're suddenly talking about lower bounds on the sectional curvature. What can we say about lower bounds on the Ricci curvature? What will happen if you replace here sectional curvature by Ricci curvature? And shortly after this was proven, Joe gave an example with a lower bound on the Ricci curvature that shows that, yeah, don't even think about that. There are Riemannian metrics on Rn. So there are Riemannian manifolds that are diffeomorphic to Rn that have all of them a uniform lower bound on the Ricci curvature. They are equal to Rn outside of the unit ball. And by equal, I mean like not just diffeomorphic. They're like literally the same manifold outside of the ball of radius 1. And all of these share a lower bound on the Ricci curvature, but they converge in the Gromov-Hausdorff sense to a space that is not a topological manifold. So this is clearly something that cannot happen in when you have a lower bound on the sectional curvature, but he managed to do this deformation in a very local way, that destructs the manifold topology while at the same time respecting the lower bound on the Ricci curvature. So he constructed spaces that at the tip of the cone in here is the cone over. So this is done in dimension 4. This can be done with n bigger or equal than 4. I guess I should have stated that if you're in dimension 3 or less, this cannot be done. And at this tip of the point, if you do this in dimension 4, you will see what you get if you take an embedding of RP2 inside R4, like just an isometric embedding of RP2 in R4, and then collapse that RP2 down to a point. What you get if you do that process is something that is not simply connected. And sorry, not a manifold. I was thinking about it's the cone over something that is not simply connected, and therefore it's not a topological manifold. So yeah, Joe basically said, yeah, if you replace sectional by Ricci, you don't have any topological control, even if the sequence doesn't collapse. But when the lower bound on the Ricci curvature happens to be close to 0, so in the case when we replace an arbitrary lower bound on the Ricci curvature by some fixed number that is very small, then we can recover this homeomorphism. So if you have a sequence of Riemannian manifolds homeomorphic to the n-dimensional torus and almost non-negative Ricci, then any Gromov-Hausdorff limit is again homeomorphic to some lower dimensional torus. This theorem will be very easy to prove if you replace this minus epsilon by a sequence that depends on I and converges to 0. But if you have a fixed number, then it's actually more delicate. And when we have it like this, we can combine some results that Jaime Santos, Rodriguez, and myself obtained with results by Chigger and Colding to essentially arrive at the point where Breuer, Naver, and Semola were, where we show that the space is homotopy equivalent to the m-dimensional torus for some m. And then the difficult part is showing that X is a topological manifold, which breaks down if you lose the tightness of the Ricci curvature. If you replace your almost non-negative Ricci curvature by an arbitrary bound on the Ricci curvature, you lose the topological manifold part. So the challenge here was to prove that the limit was homeomorphic to a topological manifold, and the key to that was basically showing that quotients of Reifenberg spaces were Reifenberg spaces. So what is a Reifenberg space? It's the last definition, I promise. When you have parameters n rho and epsilon, we say that a space is n rho epsilon Reifenberg space if any ball in your space of radius less than rho is Gromov-Hausdorff close to the ball of the same radius in Rn, essentially saying that when you pick a ball of radius smaller than rho and rescale it to have radius 1, then it will be epsilon close to the ball of radius 1 in Rn. So basically your space looks like Rn everywhere at all scales smaller than rho. And this is relevant because Chigger and Colding prove that for each m there is epsilon such that if you take a Reifenberg space with these parameters, it's for free a topological manifold. So the key in here was showing that if you have a compact Reifenberg space, that is n rho delta Reifenberg space, if delta was small enough, depending on your dimension, then its isometric group is a Lie group. And if you have an abelian a group of isometries acting freely, then the quotient is again a Reifenberg space. I put abelian in here because that's what I have been able to prove, but I believe that I can remove it. I just like haven't worked out the details of the proof, so I just left the hypothesis in here. And with that, we are able to show that in this theorem, X is actually homeomorphic to a topological manifold, and therefore it's homeomorphic to some torus. But this result was recently kind of like improved by Rong, Xiaochun Rong, who proved that if you have a sequence of manifolds, again with the same hypothesis, homeomorphic to the n-dimensional torus, and a lower bound on the Ricci curvature, now the lower bound on the Ricci curvature is arbitrary, then under the additional hypothesis that the universal covers are Reifenberg spaces, then any Gromov-Hausdorff limit of the base spaces xi's is again homeomorphic to some torus of lower dimensions. So in here, they, of course, need to put some additional hypotheses because by Joe's example, if you just delete the Reifenberg hypothesis, the theorem would be false. But he managed to work with this condition that he has been working with for for a long time, to basically obtain this homeomorphism between the limit space and the m-dimensional torus. And what he actually obtained was something very similar, like this analog statement, but for nil manifolds. So what Rong actually showed is if you have a sequence of Riemannian manifolds homeomorphic to a nil manifold with this lower bound on the Ricci curvature condition, then any Gromov-Hausdorff limit space, provided the universal covers are Reifenberg spaces, then the Gromov-Hausdorff limit is going to be again a nil manifold. So if you replace the torus in here by nil manifold, Rong's result still holds. And I'm very happy about this because now we can have a full diagram of like that answers the question. If I have a sequence of Riemannian manifolds with a lower bound on the curvature, and I take the Gromov-Hausdorff limit, is that Gromov-Hausdorff limit a torus? Then we can answer the question when the dimension of the limit space equals the dimension of the spaces in the sequence, when the limit space has dimension 1, when the lower curvature bound is close to 0, when the dimension is less than 4, and then the last condition is asking if the spaces xi are smooth, or in the case when we are working with Ricci curvature, then we have a similar diagram that basically says if you're working in dimensions less than 3, then yes. If the lower Ricci curvature bound is close to 0, then yes. And if the xi's have this reverse Reifenberg property, meaning that the universal covers are Reifenberg, then yes, by this recent result by Ron. And if not, then we have this cute example by Joe that says that don't even dream about that. So I think that's where I would like to end my talk. Thank you.
Thank you very much, Sergio, for this very nice and interesting talk. So, thank you. And well, so are there any questions? So I'm not sure if you can see us now.
I'm trying to. Okay, I can see you. Yes.
Yeah. Oh, okay. Perfect. Yeah. So I have a question, although I think you sort of answered it at the very end. But I mean, all of these results are for tori, right? But if you take then just nil manifolds, I mean, if you say take just flat manifolds, can
Uh,
you can you?
so, for example, flat manifolds, the question becomes really difficult because
Mhm.
very simple examples show that you cannot just replace tori by flat manifolds. The very simple example is take the Klein bottle. There are metrics on the Klein bottle that have 0 sectional curvature that converge to an interval. Just take the Klein bottle, that's the usual square, and you just
Mhm.
like collapse one direction. And then the quotient is
Mhm.
going to be an interval. So Xiaochun Rong, when he proved this theorem, he
Mhm.
also conjectured that if you put a certain condition on your fundamental groups of your sequence, of course, we need to assume that the spaces are aspherical or Eilenberg-MacLane spaces. Um, if you put some conditions on the fundamental group, then the limit has to be a topological, an aspherical topological manifold again. And the condition on the fundamental group was very technical. I actually don't understand it, and I think I don't remember it very well, but it was some form of like you have some for any solvable. Let me see. It's very. I mean, this is just like a first version of his of what he conjectures. Like he it's not like a solid claim. He's just like his guess, right? That if you take any normal virtually nilpotent, so a group, uh, so that's the hypothesis. The fundamental groups of these xi's have the property that any normal virtually nilpotent subgroups, uh, then any finite subgroup of the quotient is virtual normal, meaning that its normalizer have finite index. So it's some condition that he has been able to like work with well so far, but I do not like endorse it. Like I do not understand it, and I cannot say that, oh yeah, this is like the right condition. But there is a condition of the fundamental groups of the spaces that he believes to be the correct one. So yeah, it's very delicate.
I see. Thanks. And actually, in this also in your theorem, I mean, would you expect diffeomorphism? I mean that you can improve it. Is that
That is a good question. Phew. Mm, well, in here you don't get regularity of the limit, right? So no. No. It's not the limit is not going to be smooth. So I will have to stick with homeomorphic.
mm,
It's good in this specific case, it's going to be Reifenberg space, so you will have some nice regularity, but it's not going to be not even C1.
mm, okay, and lower regularity, like some type of regularity? Can you?
Mm, well, as of right now, I what I have been able to get is just the Reifenberg condition.
The Reifenberg. Yeah.
Gives like some other stuff like some bounds on the isoperimetric profile near zero that it resembles the isoperimetric profile of the Euclidean space. Um, and other stuff that is granted but by the Reifenberg condition, but again, all of it's basically direct consequence of the Reifenberg condition, nothing
Mhm.
than that.
Okay. Well. Okay. Well. Thanks. And I don't know if there are other questions from the audience, or there's also I think some. Thank you for the very nice talk. Yeah, in the comments in the chat. So, uh, well, if there are no further questions, then maybe we can. Yeah. Thank you very much, Sergio, for the talk, and thank you everyone for joining. And we hope to see you again in the next yeah next talk
Thank you.
for
Thank you all.
the seminar. So thank you, Sergio. Yes, very nice.
Thank you for going.
We can. I'll just stop the recording here. Uh, record directions here. Record.